To demonstrate we really do have contamination and propagation delays, I have here two inverters. Here's the first inverter, here's the second inverter. The first inverter is being driven by an ideal voltage source, so we don't really have true delays here. We're forcing the gate to be whatever we want it to be. We're going to look at the input signal here and the output signal here. Since we're going through two inverters, the output should ideally be identical to the input, but if we do have delays, we'll find that the output is a delayed version of the input. Let's run this and have a look at the input waveform and the output waveform. We notice a few interesting things. Firstly, we've got these spikes here, these transient responses, which are a bit of a surprise, but that's because the FETs, inside the FETs, we have some parasitic capacitance, and when you suddenly change the input, the voltages can't react immediately, and you can get such phenomena occurring. In terms of the delay, that's largely from the output looking like a resistor and the input looking like a capacitor. So we expect to see a typical voltage waveform of charging up a capacitor. And indeed, this is exactly what we see here. And on the way down, discharging the capacitor. On the way up, charging the capacitor. On the way down, discharging the capacitor. And it's these charging up and discharging of the capacitor curves that causes both the contamination delay and the propagation delay. Precisely, if we have a look at 1.2 nanoseconds, the input changes here on this green line. The output initially doesn't rise up above the V output low place. So we do have a contamination delay. It's a small amount, but the input's changed. The output has not changed yet. It hasn't risen above the crucial threshold for us to notice that the output's no longer a logic 0. The output, as it rises further, it goes from being a valid logic 0 to being in an invalid state, and then finally it reaches a sufficiently high voltage that it's deemed as being valid again, representing a valid high this time. And so the time from when the input became a valid high to when the output becomes a valid high, that is the propagation delay. Well, the propagation delay is a promise that the time it takes to go from here to here will be at least as great as will be strictly less than the propagation delay. So the output is guaranteed to be valid after the propagation delay has expired from when the input has become and remained valid again. So the distance from here to here is going to be less than the propagation delay for this logic gate. One more thing we can look at is what happens if the input consists of very narrow pulses. So we've said before that a simple model of a logic gate is one that uses an inertial delay because it eats short pulses. We can check whether or not this is true. So let's go back to our diagram, and we need to modify our pulse. Right-click the pulse. Rather than a square wave, we want to change into a very sharp pulse. So we're going to have a 50 picosecond delay just to let things equalize. We need a very fast rise and fall time because we're going to be using a 5 picosecond pulse up here. We are also going to change our transient response to be 100 picoseconds only. We now go to simulate this, look at the input, and we get a nice, very sharp peak here that doesn't last very long, only 5 picoseconds. Let's have a look at the output. So remember, if we just have an ordinary delay, the output should just be a delayed version of the input. But if the output never gets above a volt or so, that means that the logic gates have basically never acknowledged that the input has changed. If we look at the output, and we see that indeed this input pulse has been swallowed up by the logic gates. The output never goes above the threshold required for the output to have changed from a logic 0. Provided the output is lower than V output low, it's a valid logic 0 output. And so in this case, we see that despite the input having become a valid logic 1, the output has never changed from a valid logic 0. And that's why, to first order, we use an inertial delay and not a transport delay to model logic gates.